All right, welcome back. CSE 215, Lecture 3A, continuing talking about set theory. And I want to introduce a concept which is something called a membership table. And a membership table is something that we can use to help us study and learn about identities related to sets. And the idea is pretty straightforward. So suppose we have two sets, A and B. Well, we can form a table as follows. So we're going to list our two sets, A and B, and we're going to consider any element in the universe. Okay, any element in the universe. Could be part of A, could be part of B, might be in both, might be in neither. Okay, so given any element X, so X is something in our universe, there is exactly two possibilities. It's possible that X is not a member of B, or X is a member of B. And we're going to represent those two possibilities with a 0 and a 1. So if I write a 0 here, what I'm saying is that there's an element X which does not belong to B. But if I write a 1 under the B column, I'm referring to an element that is a part of B. Now similarly, an element X could be a member of A, or it might not be a member of A. And if I consider A, it's possible that X is not a member of A, or X could be a member of A. And for each of those, there's two possibilities for B. Okay, so let me say this differently. Given any element X that belongs to the universe of all possible things, there's four possibilities if we consider sets A and B. The first possibility is X does not belong to A and it does not belong to B. Or X does not belong to A but does belong to B. Or X is in A but not in B. Or X is in both A and B. And whatever element we think of, whatever X we choose, exactly one of these four conditions will apply. Right? Either X is in A or it's not in A. And for each of those, either X is in B or it's not in B. So there's only four possibilities. Okay, now suppose that I know that I have two sets A and B, and I think about the union of A and B. I can fill in this column of my membership table based on what's in these two columns. For example, if A is not in A and if X is not in A and it's not in B, it cannot be in the union. So this would be a 0. But if X is not in A, but it does belong to B, is it in the union of A and B? Absolutely. And if it belongs to A but not B, well, the fact that it belongs to A means that it's in the union of A and B. And even more so, if X is in both A and B, it's definitely in the union of A and B, because to be in the union, it only has to be in at least one of these sets. So here's a membership table for A union B. And I can make a membership table for the complement of A union B. Suppose X is not in A union B, is it in the complement? Well, the complement is everything that's not in A union B, so X would be in this set, so this would be a 1. But in all of these cases where X does belong to A union B, by definition of complement, it does not belong to the complement, because the complement is the stuff that's not in here. Since X is in here, X is not in the complement. So we're creating a membership table. And I can keep going. I can look at the complement of A, and if X is not in A, it's in the complement. And if X is in A, it's not in the complement. And I can do the same thing for B. If it's not in B, it's in the complement. And if it is in B, it's not in the complement. And this should start to look like truth tables from Engineering 250, right? This is the truth table for an OR operation. This is an inverse. It's taking the inverse of this column. This is taking the inverse of column A. This is the inverse of column B. What about intersection? Well, intersection means for something to be in the intersection, it has to be in both sets that we're intersecting. So if X is in this set and it's in this set, it's definitely in the intersection. But if it's not in B, or it's not in A, or it's not in either set, it cannot be in the intersection. Well, we just proved De Morgan's theorem, because look at what we've got. For any element in our universe, we know that exactly one of these four conditions applies. And in each of these conditions, membership in A union B bar is exactly the same as membership in A bar intersect B bar. In other words, X is a member of this set if and only if X is a member of this set. Our definition of equality was exactly that. Something belongs to this set precisely when it belongs to that set, and vice versa. That's all we need to say this set is equal to that set. So with this membership table, we have proven the following. A union B complement equals A complement intersect B complement. And that's good old De Morgan's theorem. And we proved it with a membership table, which is really nothing more than a truth table. But this is a very powerful way to prove theorems about set operations. And membership tables work because for any element in any set, there's only two possibilities. The element is a member of the set or it's not a member of the set. And if we know about membership in sets, we can talk about membership in new sets derived from those sets, for example, the union or the intersection or the complement. So we'll be able to use membership tables to prove all kinds of things related to set identities, and it's a very powerful technique. All right, so some things I want to generalize. Suppose we have three sets, A1, A2, and A3. We can take the union of all three of those, and it's sort of the obvious thing you would imagine. We take all elements that are in A1 or in A2 or in A3. That's what comprises this union. And remember, unions are associative, so this is the same thing as A1 union A2 union A3. And it's the same thing as taking A1 union A2 and then unioning A3. And unions are commutative, so we could also do A3 union A1 and then union A2. Basically, the order doesn't matter, right? And that should make sense if you think about it, because to be in this union, we simply require that an element is in at least one of these sets. And it doesn't matter what order we consider those sets in. So suppose we have a bunch of sets. Suppose we have A1, A2, A3, and so on up to A10. We could write A1 union A2 union A3 and so on and so forth, but we can also use a shorthand, which is to say union from I equals 1 to 10 of A sub I. And this should look familiar from a summation symbol. We do summations in math where we say sum from I equals 1 to 10 of I squared, and we mean plug in a 1, plug in a 2, plug in a 3, and add them all up. The sum, sigma means the sum. But here we're saying plug in I equals 1, I equals 2, I equals 3, and put a union in between each of those. So this is a shorthand for the union of all 10 of these sets. And similarly, we could talk about an intersection from I equals 1 to 10 of A sub I, and it's the extension you would think. Just take the intersection of all those sets. So we'll play with this in some homework questions, and we'll see some interesting, not obvious ramifications of this notation. All right, so one more thing I want to mention in this video, and this has to do with the idea of representing sets in a computer. This is a computer science class after all. So we're going to start tying some of this stuff into computer science. So suppose that that just for the sake of doing this, we order the elements. Okay, order the elements in the universe. So we're going to talk about finite sets here. So suppose we have a set consisting of A, B, C, D, E. And well, let's say that's the universe, okay? So the set of all possible symbols is A, B, C, D, E. And we have some set in here, for example, some set containing A, C, and D. Well, here's what we can do. We can if we keep this ordering of elements in mind, we can write a 5-bit number associated with this set. And how do we do this? We write down a 0 for each of these elements if this element is not in our set, and we write down a 1 if this element is in our set. So for example, put down our ordered set of elements, right? And it's not a set in the regular sense because it's ordered, right? But we're just applying this ordering. So S contains the elements A, C, and D, does not contain the elements B or E. And so this 5-bit number corresponds to the set S. And the set S corresponds uniquely to this 5-bit number. And you can see that the order of S doesn't matter. If I thought of S as being the set D, A, C, right, I would write it as D, A, C, and these B and E are not members of S, and my coding in binary is exactly the same. So for a finite universe, I have a finite length, fixed finite length binary code corresponding to every single set. So if I have just the set C, that would correspond to the code 00100. If I have the singleton set E, that would correspond to the code 00001. So what's the coding for the empty set? It's all zeros. And it's saying A is not a member of the set, B is not a member of the set, C, D, and E are not members of the set. And if I want to describe the entire universe, coding for that is a set of ones. And it's basically saying each one of these elements belongs to our set. Well, that makes this set the universe. And the nice thing about this representation is that we can apply our set operations, union, intersection, complement, by doing the same thing to these Boolean numbers. So for example, suppose S equals this set ACD, and suppose T is equal to the set AD. So T would be written as A, B, C, D, E, and S is 1, 0, 1, 1, 0. So if we want to intersect them, we do a logical AND. So 0 and 0 is 0, 1 and 1 is 1, 0 and 1 is 0, 0, 0, 0, 1 and 1 is 1. This should be the intersection of T with S. And this corresponds to the set AD. And sure enough, that's the intersection of S and T. And when we want to do a union, we simply take the logical OR of our two sets. And when we want to take a complement, we just complement each bit. So we'll play around with this in some homework during class also, and you'll see that this binary coding maps perfectly to this idea of sets, as long as we temporarily assign an ordering to the elements of the universe. And it doesn't have to be a finite universe. These could be infinitely long bit strings, and we could talk about sets like a set of integers and so on. All right, so next video we're going to talk about functions.